Hi everybody. Today I'm going to talk to you guys about analyzing force versus time graphs. This is important to do when you're analyzing a real-world situation, and in typical real-world situations, the force is variable. And so as a result, we end up with a difficult time trying to find what the average net force is unless we have a data table or a graph. And if we have a graph, then this is what we want to do to be able to figure it out. Now, to be able to handle this problem, it's crucial that you remember that the impulse is equal to the change in momentum. An impulse causes a change in momentum. And remember that the impulse is the force times the time. That's the cause. And then the effect is a change in velocity, typically. Typically, we don't have a change in mass as an effect. And so we do change the momentum, but typically that means a change in velocity. So far we've been dealing with what we would call a constant force, or a constant average net force. So in this case, we have a constant average net force of 400 newtons applied over 7 seconds. And so you can see that the impulse is equal to 400 newtons times 7 seconds, which is 2,800 newton seconds. Now, what does that mean? That means that the momentum will be changed by 2,800 kilogram meters per second, because impulse and momentum are equivalent. If I wanted to, instead of, I don't know why I would do this, but if I wanted to, I could go ahead and take the area under the curve, and it would give me the same information. It would give me the impulse, which is equivalent to the change in momentum. So if I wanted to, I could make that into a rectangle, and I could say, oh, okay, well, what's the area of a rectangle formula? Well, it's base times height. What's the base measurement? Well, it's the measurement along the base of it, which is 7 seconds. And what's the height? It's 400 newtons. That's the y-axis right there. So you can see when you multiply those two together, you end up with the exact same number. So everything's great, right? So you have two different options for how to do this. Again, there is a different option for trying to do this if you have a variable force, which usually involves a table, which you're going to see later on. But for now, we're going to restrict ourselves to what happens if you only have a graph. So that's the important point. Anyway, so the key point here is the area under the force versus time curve is the impulse, or the change in momentum. It becomes especially important to remember that when you're dealing with a changing force, because if the force is changing, then sometimes it's hard to figure out what the average velocity is, or excuse me, the average force is. And so you have to kind of use the graph as the thing that guides your work. And so we need to either be able to calculate what the average is from the graph, or we need to be able to use a different strategy to solve it. And in this case, the strategy that I've chosen to use is the area under the curve graph of the force versus time graph. So I've drawn a changing force. You can see it for the first 2 seconds, it increases steadily, and then it plateaus for the next 3 seconds, and then it decreases for the final 2 seconds. So I could try to figure out a way to calculate the average force over that period of time if I wanted to. It's not terribly difficult, but it is much easier with a data table and with a spreadsheet, because you know I love the spreadsheets. So maybe a better option in this case is to try to find the area under the curve. Now it just so happens that that particular shape is a trapezoid. Now a trapezoid is kind of a weird shape. If I really wanted to, I wouldn't have to consider it a trapezoid. I could actually say it's a triangle and a square, or yeah, a triangle and a square and a triangle, or a triangle and a rectangle and a triangle if I wanted to. But it's much easier just to do the whole trapezoid by itself. So that's what I'm going to go ahead and do. Now, a trapezoid has this weird shape where it has 2 different bases and 1 particular height. And so the area of a trapezoid formula is 1/2 times base 1 plus base 2 times the height. And so I can go ahead and plug those numbers in. Base 1 here is 3 seconds. Base 2 on the bottom there is 7 seconds. And then the height is 300 newtons. And if I plug all that stuff in, I end up with an area of the trapezoid of 1,500 newton seconds. I think that's way easier than trying to figure out what the average is first, and then going ahead and multiplying that average net force by the time, which is 7 seconds. Again, I think that's way easier sometimes. So it's definitely an option you want to use. Now, how would I apply this? Well, let's imagine that we have that impulse applied to a mass of 10 kilograms. How much change in velocity results? And so I know that the impulse is 1,500 Newton seconds, and we're trying to find delta V, and we know mass is 10. So I'm going to go ahead and write those in. So the impulse, which is the left side of the formula, I can go ahead and summarize as 1,500 Newton seconds, since I already calculated that. And that's equal to 10 times the change in velocity. 10 is the mass, and so I can divide both sides by 10, and I end up with a change of 150 meters per second. And so that's how much that velocity changes over that time. Thanks for watching.